Our final speaker this morning is Justin Kunimune. He studies fusion at Massachusetts Institute of Technology, and he performed his 2 residencies at Lawrence Livermore National Laboratory in 2023 and 2024. Please, take it away.
Thank you. Yep, I'm Justin. I just graduated from MIT. My advisor was Johan Frenier, and I defended my thesis just this past month. And thank you so much to the NNSA and the LRGF for funding my thesis. So yeah, I'm going to talk about inferring residual kinetic energy in ICF implosions using heterogeneous data and neural networks. And I'd like to thank my sponsors from various institutions, especially other people at MIT and many people at LLNL and the DOE NNSA. So the overall summary is that we have developed a way to combine heterogeneous neutron data sources at the National Ignition Facility to infer residual kinetic energy. Residual kinetic energy is a major degradation factor in current ICF experiments at the NIF, and it can't be directly measured. So in order to try to diagnose it, we've developed a new method to reconstruct 3D morphologies of NIF experiments using a suite of heterogeneous neutron data. A rocket piston physics model is used along with Markov chain Monte Carlo and a neural network surrogate model to find simulations that match the data, and we've thus concluded that the residual kinetic energy of this NIF experiment from 2024, June 28th, is about 2% of the total implosion energy, which we think reduced the yield by about 35%. So I'll get into it now. First of all, I know Ben kind of gave an overview of ICF earlier, but just to orient us, in inertial confinement fusion, fuel capsules are spherically imploded using lasers to extremely high densities and temperatures. And once you've reached the point of peak compression in your implosion, it looks something like this, where you have a very low density remaining ablator around the outside, surrounding this very hot spot at the center where fusion reactions are taking place of a DT plasma, and then a relatively colder and much denser DT plasma around that, which forms this dense fuel shell whose inertia confines the hot spot. And so an ideal ICF implosion looks like this, where it's all perfectly spherical, and all of the energy is concentrated in the hot spot, which then initiates the fusion reactions that propagate outward into the fuel. In practice, implosion performance is often limited by various degradation factors such as 3D asymmetries, which make it not spherical. Just as an illustration, something like this is a more realistic and non-ideal ICF implosion. I mean, it's not usually this bad, but just to kind of illustrate, it's bad if it's not perfectly spherical because that results in residual kinetic energy being left in the shell at the time of minimum volume. So that's energy that is kinetic energy in flows in the shell, which is not being converted into internal energy in the hot spot. Because it's not heating the hot spot, it's effectively wasted, and so the presence of this residual kinetic energy severely reduces the implosion's neutron yield. And so here's a plot from a paper by Annie Critcher where it shows some simulated ICF implosions with the neutron yield on the y-axis and then the amount of residual kinetic energy on the x-axis. And you can see that as the residual kinetic energy increases, at some point you cross below the ignition threshold and your yield very sharply drops off. And the residual kinetic energy cannot be directly measured because it's such a dynamic and three-dimensional quantity, and that makes it really hard to gauge how big of an issue it is and how we should change the experiment to avoid it, because like I said, it has this very strong effect, but we can't actually measure the x-axis. Multiple diagnostics currently provide data that's used to probe asymmetry and residual kinetic energy, but they're all inconsistent with each other. So for example, we have the neutron imaging systems, which record primary and downscattered neutron images from multiple lines of sight. We have the neutron activation detectors, which measure primary neutron yield on 48 lines of sight, and so that gives you a measure of the variation in the areal density of the shell. And then we also have neutron spectrometers on multiple lines of sight, which give you the downscatter ratio, which is a measure of the overall areal density of the shell, as well as the hotspot velocity vector, which is a measure of asymmetry. And so these are all useful and provide lots of useful information. But if you analyze each one individually, you can extract a residual kinetic energy from each one, but they're all inconsistent with each other because of the fact that each one is only probing part of the implosion and seeing some of the asymmetry modes. And so this indicates that these diagnostics individually none of them provide enough information to fully understand the problem. And so a new method is required that accounts for all available data and provides a single self-consistent 3D dynamic picture of the implosion. And so that's what we're developing. We use a forward fit to the rocket piston physics model to combine these heterogeneous data to create that single unified picture of the implosion. The rocket piston physics model is a very simplified model of an ICF implosion that combines existing models for the Hall-Rahm radiation and the ablation rates, power balance in the hotspot, and the dynamics of the imploding shell. And so you tune a few inputs like the initial pressure and the laser energy and perturbations to the shell shape, and it gives you a complete model of the implosion from the laser turning on to stagnation in a matter of seconds. And yeah, so compared to other codes that people use for ICF implosions like Hydra or X-Rage, it's relatively fast and provides you with quite a lot of information since it models pretty much everything. And so here's just an example of some synthetic data that comes out of this model. This is a fluence compensated downscattered neutron image. And so, yeah, we have this model. It allows us to generate synthetic data for some set of inputs. And then we use Markov chain Monte Carlo to find model inputs that fit the synthetic data to the actual observed experimental data. So Markov chain Monte Carlo, for those who don't know, is a stochastic iterative optimization algorithm. It executes the model thousands of times with random perturbations to try to find a set of tries to find all sets of inputs that generate synthetic data that is consistent with the observed data. And because it requires thousands of executions of the model, it's pretty slow. The rocket piston model is quite fast, like I said. It only takes a few seconds, but if you need to do that thousands of times and you also need to calculate gradients and it's not auto-differentiated, then it gets kind of intractable. And so for that reason, we use a neural network-based surrogate model to speed up the calculations. Well, all we're doing here, our surrogate model uses the MAC architecture, which was developed at LLNL. It's an architecture that uses multiple neural networks to mimic a physics model like this one to generate synthetic data. And what we do is we train it on 100,000 random executions of the rocket piston model with random combinations of the input parameters so that for any given set of input parameters, you can plug it into the surrogate model instead of the rocket piston model and get the same result. Except that the surrogate model is, of course, differentiable and invertible and much, much faster than the actual physics model. And so here I'm just showing comparisons of some primary neutron images generated by the rocket piston model and the trained surrogate model for the same sets of inputs. You can see they're a little bit different. There's, in particular, a little bit of noise in the surrogate model images, but overall it gives very similar results, which gives us confidence that we can use the surrogate model in lieu of the rocket piston model in the sampling. So to demonstrate how this works, a reconstruction of that shot I mentioned, N240628, is performed by incorporating all of the heterogeneous neutron data available. So on this shot, we have 3 neutron images. There are two primary images from 2 different directions. So those are images of the burning hotspot. And then we also have this fluence compensated downscattered image from one direction, which is approximately an image of the dense shell surrounding the hotspot. And we also have the neutron activation diagnostic data, which again measures the primary neutron yield on many lines of sight, and so shows low mode asymmetries in the areal density of the shell. And then we have the hotspot velocity and the downscatter ratio from the neutron spectrometers. So we plug this all into our sampling and our surrogate model, and we get this fun 3D blob. So here's the hotspot boundary in 3D, and then we can also reconstruct the fuel shell surrounding the hotspot. So in terms of actually interpreting this, what we really care about is, of course, residual kinetic energy. And for the first time, this allows us to reconstruct ρr asymmetries and residual kinetic energy up to modes L equals 5. So just to orient people here, this is breaking down the residual kinetic energy into different spherical harmonic modes. So L equals 1 represents like a translation in the hotspot geometry. So that means that there's some non-zero velocity in the center of mass at peak compression. L equals 2 means some kind of elongation or oblateness in the implosion. And so there's 5 different modes because there's essentially 5 axes that you can elongate it on. L equals 3 means it's triangular in some sense, and there's 7 different modes in which it can be triangular, and so on. And so what we're showing here is breaking down the residual kinetic energy into the specific shape perturbations that are causing it. And so you see here that the most of the residual kinetic energy is contained in these 2 modes, L equals 2, M equals 0, which is known to be a very common problem child at the NIF. It's elongation or compression along the z-axis. And then this other one, L equals 3, M equals 2, which is a tetrahedral mode, I believe. And this is not something that people usually talk about, so it was kind of surprising to see this in the result. But the sampling is quite confident that the data does show the signatures of this mode. And this is actually something that we're finding on multiple high-yield NIF implosions. So that's very interesting that we were able to extract this by combining the data, even though it's not super apparent by just looking at any individual piece of data. And yeah, and then I don't have it written here, but we also can calculate the total amount of residual kinetic energy, which is about 2% of the total implosion energy. And by running the rocket piston model with these modes suppressed, we think that that reduced the yield by about 53%, which is pretty substantial, and actually theoretically prevented this particular implosion from reaching net target energy gain or ignition. So just to summarize, we've developed a way to combine heterogeneous neutron data to infer residual kinetic energy in implosions at the National Ignition Facility. Residual kinetic energy is a major degradation factor in current implosions, but it can't be directly measured. So to diagnose it, we've developed a method to reconstruct 3D morphologies from heterogeneous neutron data. We use a rocket piston physics model along with Markov chain Monte Carlo and a neural network surrogate to find simulations that are consistent with the data, and thus find that the residual kinetic energy of this particular experiment is about 2% of the total implosion energy, which reduced the yield by 53%. Yeah, thank you.